Previously, we've learned about electric potential energy in general. This time in this video, we're going to learn about how to derive an expression for the electric potential energy specifically for point charges. So what we're going to do is we're going to think about starting with two particles. We'll call them Q1 and Q2 that are infinitely far apart from each other. We're going to assume Q1 to be fixed in place. So let's say that Q1 is located here. And we're going to say that Q2, again, starts out infinitely far apart, really far away from Q1. And we're going to think about bringing Q2 closer to Q1. So it's as if there's an external force that moves this Q2 closer and closer to Q1. The potential energy of the system would be equal to the work that has to be done by some external force to assemble the system. In other words, to bring Q1 and Q2 closer to each other. So we know that work done by some external force would be equal to the positive change in electric potential energy. Positive this time because our external force, if we think of these as being two positively charged particles, would have to be in the opposite direction of the electric force. And we also know that the change in electric potential energy is Q times the potential difference. In this case, Q2, since that's the one that we're actually moving. We can also say that the initial potential energy is equal to 0, thanks to the fact that that Q2 started off infinitely far away from Q1. So at infinity, we say that the electric potential is 0. So then this tells me that the final electric potential energy would be equal to Q2 times V final. And we already know that we have an expression for the electric potential thanks to a point charge. That's K times Q1 over R. I'm using Q1 here because I'm thinking about the electric field set up by Q1 at the location of Q2, kind of my final location of Q2. So this helps us kind of finalize an expression. And even though we used kind of a general scenario here, this is an expression that we can always use for electric potential energy when we have point charges creating a field. That expression says that the electric potential energy at a given point, instead of saying UF now, I'm going to say U sub E, is K Q1 Q2 over R. You'll notice this expression is pretty similar to the expression for electric force. However, there are no absolute value signs in this expression. And what that means is that if Q1 or Q2 are negative, you want to make sure that you plug in a negative value for those charges. So again, looking a little bit further about the types of charges that we could have here. If the charges do have the same sign, we have to do positive work to push them together against their repulsion. If they have opposite signs, we have to do negative work. And again, when I say that we have to do negative work, I mean that there must be some external force doing negative work or some external force doing positive work. One last fact about this a couple more facts rather. So one thing that you may commonly see with electric potential energy is a unit for energy that's not the same as joules. We know all energy can be measured in joules. But there's another unit that we sometimes use when we're dealing with very small bits of energy, as we often do here as we deal with point charges. And that's called an electron volt. The conversion factor that you need to know is that 1 electron volt is equal to 1.602 times 10 to the negative 19th joules. That number should look familiar to you. It's the charge on an electron. Basically, we came up with this unit, an electron volt, by taking the charge on 1 electron times 1 volt. And when I do Q times V, I get joules. As you can see in this equation, up here that the change in energy is Q times delta V. Lastly, if you have multiple point charges, the potential energy of the system is the sum of the potential energies for each pair of charges. That last fact is going to become really clear as we look at an example problem. This is problem number 43 in your textbook. We have 4 point charges, 2 that are plus Q and 2 that are minus Q, arranged in a square with a side length of A. We're asked to find how much work is required to set up this arrangement if all of the particles start out initially infinitely far apart. Basically, the idea here, or another way of asking this would be, what's the potential energy of my system? And to find the potential energy of the whole system, we would need to find the potential energy of every possible pair. In other words, if I label these 1, 2, 3, and 4, the potential energy of my system, which again would be the same thing as the work done by some force. Really, if I'm doing the work done by the external force, we know that that's the positive change in potential energy of the system. And we're going to say that initially they're all infinitely far apart. So that tells me that this would be equal to the final potential energy because the initial would be 0. To get this value, I have to add up several different values for potential energy. Specifically, the potential energy that particle 1 and particle 2 have, plus the potential energy between particle 1 and particle 3, plus the potential energy between particle 1 and particle 4, plus the potential energy between 2 and 3, plus the potential energy between 2 and 4, plus the potential energy between 3 and 4. I have 6 possible unique pairs here. This is a great example of where it's significantly easier to do this problem in variables before plugging in numbers. So what I'd like you to do to finish off and bring to class with you next time we meet is to come up with an expression, write an expression for each of these potential energy pairs. I'll even start you off with the first one. Add them together and find a numeric answer given the amount of work that's done to set up the system. For example, for particles 1 and 2, we have K. Q1 is positive Q and Q2 is negative Q. So Q times Q we know is Q squared. There's a negative sign in there. And they're located a distance A apart from each other. I'm going to use that same method to develop an expression for each of these potential energies, combine like terms, and then plug numbers into the solution.